So let's suppose that we've replaced the transistor in our NOT gate with two Nmos transistors that are in series, right? They're connected like this. And so, obviously, given the title, we know this is going to be a NAND gate, but let's run through all the possible situations and make sure it actually works like a NAND gate. So, we're going to start being a little bit more abstract here. We know we've just got a voltage here. I could have just put a plus there, right? Plus, plus, plus. This is our 0 or ground. And then we're just going to deal with ones and zeros. We're not even going to care about our resistances. We'll just say that it's a suitable resistance, maybe 1,000 to 10,000 ohms, maybe more. So let's look at this first scenario where we have two zeros coming in. So if we have two zeros, what that means is this, right? Thinking of these as controllable switches, both of these are open. And so that means that ground cannot get to this output, or 0 can't get there. And so that means in this case, the 1 wins. So our output is a 1. Now, our next scenario, right, is a 0 and a 1. And in this case, our 1 means that this is closed here. This one's still open. And so you could kind of think of it, right? This isn't necessarily strictly what's happening, but you can kind of think of this as the signal of ground trying to get there. And it can get over this bridge, but it can't get past this bridge because it's too big of a resistance. And so in this case, the voltage source, right, the plus or the 1 is able to get out, and so we have a 1 in this case. And based on the way this device is wired, you'd expect that the inputs would kind of be commutative, meaning we could switch them around. So if I had a 1 here and a 0 here, it's still kind of the same situation. We've got a closed signal here, but this guy is open, and so ground can't really get anywhere further. It can't get to this node. And so once again, our voltage is able to win. So that means we get a 1. And last but not least, if we have two 1s here, that means that both of these transistors are closed, right? So you've got a connection here, you've got a connection here. So that means that ground is able to get to this output or this middle pin, and while V is, it is not as strong as this ground because there's no resistance there. Once again, you can refer to our voltage divider expressions to understand that. And so that means that our output is 0 here. And in this case, right, we can write our truth table where we could just call this row A and this row B. Right, we can just, well, here, I'll just do it. So 0, 0, 0, 1, 1, 0, and 1, 1. This is A, this is B, and our output, right, our thing in between devices where we've got transistors and then the resistor, this is always going to be our output. And so we've got a 1, 1, 1, 0. And sure enough, this is a NAND gate, right? This is a NAND gate.